everyone. So I would like to share a use case, one of the recent use cases completed engagements on applying prescriptive analytics for recovery improvement. Maybe just a few words to set up the context. We have been working with a base metal concentrator who has been struggling with declining performance over the last 12 months. From the moment we started, they had multiple issues, really ranging from stockpile, blending, processing, so yield and grade. The biggest issue was output variability on both recovery and on grade and on the total concentrate produced. One of the structural issues at the client was the highly variable ore composition, which could change really from day to day, and the problems with stockpiling did not make it easier. Another relevant thing to mention is that the client has been focusing on improving throughput. Of course, conventional wisdom says if you have the lower throughput, if we lower the throughput and we try to maximize, the recovery will be higher because we can grind our ore finer. So here there were multiple initiatives maximizing throughput, but as a consequence, the variability of the throughput and also of the stress on mining circuit and crushing circuit was so high that it just facilitated output variability. So one of the important outputs, maybe of insights of today's webinar, is that we should always optimize for profitability. So here the purpose was to increase recovery while instilling a new way of working using virtual experts, which are guiding operators for optimal decisions at every minute of every hour. So maybe jumping to conclusion, what is a tangible impact and why is it an important use case to share with you? So we have obtained improvements, and it's not just at the end of the engagement, but 3 months after the engagement. The total of 6% point improvement in recovery, which happened together with a massive increase in grade, so the quantity of valuable metal in total concentrate, and increase of the total concentrate produced, while having analytics insights embedded into daily operating practices. The total impact from this engagement is $40 million additional revenue per year. And we'll be happy to share with you how we did it. So just a little more context on this. So we have focused specifically on the most difficult circuit for the plant. It was a flotation circuit. And of course, the conventional wisdom is that the most important levers that are influencing the outputs would be first of all, the feed grade, so the grade and quantity of valuable metal in our ore, the throughput rate, and the flotation circuit parameters. One of the interesting insights from this project, but also from other projects, are that set points that we're using on a flotation circuit are tertiary influencer. However, they're responsible for 40% of the variability of the output. So given the grade and given the throughput, we still have a lot of freedom to optimize flotation set points to improve the outputs, even if we got the bad ore and even if the throughput was not on target. So what we did during the engagement, so worked along these 3 pillars. First, we improved the ore composition somewhat by optimizing and reducing variances in blending and stockpiling. So what you see here at the bottom graphs are just the graphical representations of the distributions of feed grade, so on the first column. And you see that it is slightly improved versus the baseline over the 5th month of our data. The second part, which is important, is that we stabilized the throughput rate. Stabilized and reduced it slightly. By reducing the throughput rate, and of course, we know that if we run it with a low throughput, we will have high recovery, but we will also produce less concentrate, so it's not going to positively impact profits. In this case, the optimal settings for the throughput rate have been more than, the reduction in the throughput rate has been offset by gains not just in recovery, but also in the total concentrate produced and the grade in this concentrate. The last part is the planned set points, so the flotation circuit set points, which are responsible for, again, almost a half of the output. We have also significantly stabilized them. We are talking about 12 different parameters at the flotation circuit. We focused on them. And the idea behind virtual experts in general, and also in this use case, is that we can manage and change dynamically the set points on the flotation circuit given the incoming ore and the incoming throughput, grind it in a certain way to always get the best output. So how exactly did we do it? And this is an illustration of what advanced analytics and prescriptive analytics is doing. We started, so there is a schematic representation of our flotation, of the entire processing plant. On the left side, we have inputs. We took 1 year of historical data. It was more than 500 different plant variables, technological parameters, data from sensors, information from lab assays, which are showing us ore and feed properties, all calculated properties. As the outputs, which we call key performance indicators, we of course need to consider profit at first. And one of the most important factors defining profit for us would be the quantity of total concentrate. This was an explicit output that we considered. The grade in this concentrate, so what is the fraction of valuable metal in our concentrate, and then recovery and recovery variability. Again, you always get what you optimize for, and we do not want to just increase recovery for the purpose of recovery. We want to improve profit. That's why we want to consider these objectives, which are potentially competing together at the same time. Once we build predictive models, we discovered in this case that there is actually only 12 input parameters from the left-hand side that are influencing and explaining or predicting, if you want, the outputs. And these 12 are, of course, the feed grade, the throughput rate, and then 10 flotation inputs. Once we get reliable predictive models, we can use them for prescriptions. We can reverse engineer predictive models, implement them, if you want, for daily operations. So on the right, you see a schematic of our circuit. So we are interested in KPIs in the recovery that we have at the end of the flotation circuit. At any point in time, in this case, 3 hours, we set the current values from the upcoming batch. So this would be feed rate, float feed, grade, and the 10 parameters. The model at each point in time takes the values of the planned 12 parameters, and I know that I cannot change the feed grade, I cannot change the throughput rate anymore, it happens before the flotation circuit, but I can in principle go and change the flotation set points. So first of all, the model immediately gives us a prediction of the expected recovery that we will get and recovery variability in 3 hours from now at the end of the flotation. This is the first insight, an instant prediction of the result. And the second point is that it gives us the recommendation of how to change the parameters, flotation parameters, to get an improvement, an estimation for this improvement. So later on in what we can do, just if we scroll a little bit down, we see that for each moment, so each 2-hour interval when I make these predictions, we can also estimate what was the expected recovery and what is the improved recovery through dynamic changing of flotation set points. So this is a little bit how, explains you how the virtual expert operates. For technology engineers, if you scroll even down, if you want to see this information, probably would not be interesting to the operators. You can also explore. So the underlying model is not a black box. You can see in real time how would it operate and what would happen if you change any of the input parameters, so as sliders, and what would be the expected impact. And just wanted to share with you a couple of additional insights. These insights are from the same project, but again, we see this repeating in all engagements we do in metal and mineral processing. Less is more. What we often observe, and this is a graphical representation for this particular example, that first of all, so on these complex graphs, you see actually these are all plus signs, and we put a plus sign when we notice that the set point has changed. And they are sorted in the order in which of the frequency of changing the set points. You see that some of the flotation set points have been being changed every 2 hours, some others every 9 and 10 hours. But what we notice is that sometimes operators are attempting to stabilize the circuit by changing the parameters often. However, it does not improve the stability, but actually makes it less stable. And this is an illustration on the right of the actual recovery for the same time period. So the first insight is maybe we should not touch the circuit unless it is really necessary. Stability, there is a bit instability, and this is another insight of that we wanted to share from our analytics implementations. Next, just very interesting insight that we wanted to share is that less is still more. And very often we notice that when we have chemical processes, and in this case we add reagents to the flotation circuit, the optimal settings for the reagents, if we really simulate it in a certain interval, and if we look at the optimal settings and sum them up across all reagents, are 36% less, so require a reduction in reagent use for a higher recovery. So what we see here is the black line is the actual recovery, the light blue line is the improved recovery. We see that we can recover better but use less reagents. This is another, again, counterintuitive insight, and which you want the operating team to internalize and own it. Initially, it is counterintuitive, and in this case, the team went in just 4.5 months' time from the insight, we will never run our plant like this, to actually running our plant like this.